Okay, so welcome back to the channel, guys. We're on the road again today. Sasquatch Prospector here. We are heading into the Alouette Stave Ruskin power generation. So it's 3 lakes: Alouette Lake, Stave Lake, and Hayward Lake. They all form the Ruskin Stave Alouette power generation complex. We are going to go to Stave Powerhouse, which was at one point the largest power producing plant in British Columbia. Provided a lot of power to the lower mainland, everything like that. So it's really cool. It's an old powerhouse, obviously. Haunted as well, so maybe we see some ghosts. I don't know. You be the investigator as much as I. But anyways, we're just about to come into the powerhouse now. Really, really cool history. You can take a look at the outside, show you the whole facility, because it's open again. It's finally open again. It was closed for wintertime, so here we go. So here we are, Stave Powerhouse. Let's go take a look. Power in the towers. Looking at the top section of a 27-meter high transmission tower. Some of the tallest towers in the BC hydro system are 120 meters. It's pretty high. 17,800 kilometers of transmission lines transport high voltage electricity from the generating stations to the local substations where it's created. This is the transmission tower. You see the insulators there, wires going off for power, insulators, and then the cables. Fairly simple, bunch of angle iron. So this is the tower. Top section of 27-meter high transmission tower. Some of the tallest towers in the BC hydro system are 120 meters. The transmission system is designed to carry 69, 138, 230, 287, 360, and 500 kilovolts. The towers are used as cell sites for cell phone companies. Electricity travels 299,333 kilometers per second. Almost the speed of light. Not quite, but almost the speed of light. Because of all the coastal fjords in BC, we have some of the longest line spans in the world. Some crossings are more than a kilometer long. Pelton wheel, water wheel. Water comes into these chambers, moves the water wheel. Very simple. So we're currently in Alouette, Ruskin, and Stave power generation complex, the 3 lakes, series of dams, all generating power together. Transformers, squids, and primary dips. How BC Hydro gets its power to your home. The distribution pole, 4-wire service, triple phase pole top transformer bank. Those little tubs right there, that's the transformer bank. Porcelain pin insulators, 3-phase overhead primary distribution. When primary overhead distribution conductors go underground, this is called the primary dip. Surge arrestor, 3-phase dead end structure, single-phase power bear conductor, fused cutout, single-phase pole, bird guards, transformer guy wire. Squid is a connector below the ground. Service box splits the underground secondary cable into several underground service cables. Low profile transformer over there. That's a meter over there. Keeping your lights on. Alrighty, so let's get to the powerhouse. And this was the old powerhouse. It used to generate power. The new one is over there. It's more efficient. And they turned this one into a visitor center for everybody. So everybody can enjoy the interactiveness of power and all that comes with it. This place is haunted too. One of the guys running the switches in there, we'll go see him later. All right, we're gonna go to the generator hall. Okay, so the bridge crane, 60-ton traveling crane. Notice large gears that were used to drive it. 3 copper rods on the wall above provide electricity. How many parts block we got here? 4-part block and an 8-part, because you can just count the lines, right? 4-part, 8-part. More than 90 years ago, the Stave Powerhouse was completed and replacing the original. So this is the generator hall, guys. We are now in the generator hall of the Stave Powerhouse. BC Electric Railway, they bought this powerhouse and wanted to use it for their electric tramway. Ruskin generating station. In the 19th century was a golden age of electricity. Streetlights, streetcars, and lighting gaining popularity. The steam plants couldn't keep up. When the Stave project was envisioned in 1895, hydro technology was still new. Niagara Falls, the first large-scale electric plant in North America, was still struggling to work out how to transmit electricity to Buffalo 20 miles away. That was the AC, guys. At the time, now they have DC power transmission, high voltage DC power transmission, but at the time, they could only do AC. DC was really bad for power transmission, and Tesla, again, had a big part in that. By 1926, Stave Falls was the largest source of power in BC. A tunnel was built between Alouette Lake and Stave Lake to add more power. That's the Alouette Lake generating part. That's where it comes in. Every shift had 1 operator, 2 floormen who manually kept the machines running 24 hours a day, 365. So what do we got here? We got floormen, carry out, general maintenance, Foremen had no formal electrical education. Every hour they had to check machinery parts, belts, oil leaks, circuit breakers. They also had to open the spill gates and close the penstock head gates when needed. Because they only had the on-the-job training, they carried notebooks containing step-by-step instructions for complicated procedures. Formal apprenticeships began in the 50s and 60s. Running the machinery from the control panel upstairs, the operator was in charge of the station. Every hour he read the meters, recorded the power produced by the system. He also kept careful records done by maintenance. Wood pipes. Yeah, that doesn't look very fun. I wouldn't want to drink out of that. Early pigtail wrench. This wrench is used to splice copper and wire conductors together. Vaporizing liquid fire extinguishing unit. Early pole insulator. Synchronous motor clock. Really, really big facility, guys. This main turbine hall is quite fun. We're just on the upper level right now, making sure we got everything covered here. As you can see, just doing a good walk. There, you can come here and see a Tesla coil. If you want to see a Tesla coil, guys, this is a place to come see one in action. They got two. They got self-interactive one and then one that they do for show. So this is where they controlled everything, all the magic. Amp meters, volt meters, watt meters, all that stuff, phase monitoring, everything. It's all here. So what we got here, ammeter, 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 ammeter. Well, it's all amps. Watt meter, oh, we got a couple watt meters, volt meter, watt meter, power factor meter, volt meter, watt meter, power factor meter, yeah, gate opening. So this is how you control the plant. It tells you everything you need to know about the plant. That would take you outside to the penstocks. So we're gonna go down now to the actual turbines, where the turbines are. We're gonna look inside the turbines. Now, what's weird with these turbines is they're mounted sideways, which is not normal. Usually turbines are mounted vertically. They're not mounted horizontally like this. This is interesting. Oh, horizontal turbines. Units 1 to 4 consisted of horizontal turbines lying on their side that weighed 150 tons. Although vertical turbines were becoming more popular around the time at Stave Falls began operating, horizontal turbines were more easier to maintain. So it's basically ease of maintenance. They did it, but this is not actually how they do it now. The Francis type turbines were built by S. Schweiss company in Switzerland. The machinery cost 250 grand alone. And this is where the ghost, the Stave ghost could be. Buddy there was at work one day and then he wasn't. The DC room. Generators produce electricity but also require their own power to start and function. That's because they're not brushless. This power is known as direct current and is created by an exciter. The direct current generated by exciters was fed to the DC room, controlled and then distributed to the generators. Each generator had its own set of DC controls. By controlling the direct current, the operator could in turn vary the power produced by the generators. To avoid electric shock, the operator would stand on an insulation block you see in front of you and would use a wood club to move the controls. So that right there, the way the story goes is Buddy was on this insulation block and he obviously touched one of the connectors or stepped off the block and died of electrocution and supposedly now haunts the facility. But you can see that each generator, it's got its own set of controls to send DC power to basically charge the field max. Because what you're trying to do, you have field coil pack, and the field coil packs need to be charged because there's magnets inside it. You need to charge these magnets so that when you move the armature, it'll help rotate the magnetic field. So here you go. So you've got the stator, the rotor, and the spinning shaft. The spinning shaft is power from the turbine. So the water comes down through the penstock, comes into here, moves that turbine, which in turn will spin this shaft. Once this shaft spins, the rotor will start spinning with it. As the rotor spins around the stator, electrons move back and forth, and that's what creates electrical current. The magnet pack in the stator, it's the magnets that allow the electromagnetic field. If you just took two pieces of copper beside each other and move them back and forth, you need the magnets. So a generator uses wire and magnetic fields to create electricity. Wire coils called stator windings are fixed around the outer rim, which does not move. This is the stator. A rotor with another set of wire coils called field poles is turned by the turbine. The direct current from the exciter flows through the rotor and magnetizes it. When the magnets are rotated within the stator coil, it makes electrons in the coil move back and forth, which generates electric current. You see these field coils on the rotor, or the armatures, I like to call it. That's another name for it. They're called field poles. The DC current flows into the rotor and charges these, magnetizes it, so that when the magnets are rotated around the stator, electrons will move back and forth and produce electric current. The generator can't work without the turbine, so we call them a unit. Supplied by Canadian General Electric, generating units 1 and 2 were in service by 1912. As with most power plants, the generators produced alternating current. These generators were capable of producing 13,000 horsepower, 440 volts at 60 cycles. Shaft spins. It spins the rotor, which energizes the magnets in the field poles, which then moves around the stator windings, the wire coils, which causes electrons to move back and forth, which produces power. And that's basically how these generators work. So you've got the stator on the outside, the fixed part is the stator, and then you've got the rotor, which rotates around with the magnets are charged. Because the amount of power at stave falls varied, governors were needed to control the power output of the generators. The governor is the brains behind the generating unit. When the generating unit first starts up, the governor controls the amount of water passing through the turbine to bring the turbine and generator up to a constant 225 revolutions per minute. It does this by opening and closing a set of gates called wicket gates. Once the unit has reached that speed, the circuit breaker closes and connects to the generator to power the lines. After that, the governor continues to control the amount of water passing through the turbine, mainly to vary power output, because it's relative. Each generating unit has its own governor. The unit is controlled from the governor itself in the main control panel upstairs. So that's how they meter the water flow, which controls the RPM, which controls the power output. The governor is very important because they can't control the water flow and the RPM, then their power output's all messed up. A centrifugal governor, Canada General Electric, Toronto, Ontario. Power factor of 80, 3-phase, 1725 amps, 60 cycles, 225 RPM. The water comes into here, moves the wicket gates, which rotates the shaft, which then is what creates power. So let's go take a look at these exciters, because these exciters are a really, really important part of the operation. Generators produce electricity, but they are also required to produce their own electricity to function. This is known as direct current, and the current is created by an exciter. The exciter is the backbone of the generation control system. It is the source that supplies the direct current that powers the generators. Stave Falls exciters were powered by their own turbines, and the exciters are all generated 125 volts, just enough to excite the main generator. Direct current generator. Canadian General Electric, Toronto, Peterborough, Montreal. Got the commutator bar, armature, stator, field packs, field coils, commutator bar, asbestos. You got the governor too, water wheel governor, which helps control the shaft. So you can see, so water will come in here, the governor, which controls the speed of this, which controls the speed of the shaft, which for generating power. Because keeping your RPM in check is really important. Otherwise, it's not gonna go well for you. Just absolutely gorgeous, this old stuff still. Absolutely gorgeous. And basically the way it worked was 2 generators each had their own exciter. So 1 exciter for 2, 1 exciter for 2, and then there was a 3rd exciter, which the last generator had its own one. These 4 were installed first, and then they installed the 5th one down at the other end later. The 4 originals were 2 each. It was split 1 exciter per 2 turbines. This shows you what they're doing here, right? On the pump, we're shooting water at the turbine, which is generating power. We're at, yeah, there we go. Pretty cool. And as you increase the RPM, it gets more power. Pelton bucket and needle. Pelton needle valve. Control the volume of water flow. So this is the turbine, right? See, wicket gates, tail race, generator. So wicket gates in there, draft tube, rotor stator, draft tube. And then the tail race has come down under the draft tube. Governor oil pumps. The governor controls how much water goes into the turbine. The 2 pumps provided oil to the governor's high pressure system. The oil was used to help open and close the wicket gates. Small impulse turbines powered the oil pumps. Water from the turbines was supplied to the exciter by penstocks. We got another one over here. Again, 2, 1 for each governor, because there's 2 governors. So there's 2 oil pumps. And then the one down the other end there had its own. Just needle valves. Bunch of needle valves for metering flow. So we're just on the lower level now, looking through everything. The exciter. So you've got field magnets, armature coils, pull piece, field coils, and this is it's all just the interaction of these guys together. But you have to charge the magnets. If you don't charge the magnets, you can't make power. Unit transformers. Stave Falls generators produce electricity at 4,400 volts. Electricity then traveled through a circuit breaker located in front of each generator to the unit transformers. Step up the voltage from 4,400 volts to 60,000 volts and feed it to the switchyard. They take the power from here, from these generators, upstep it, and then move it to the switchyard. Circuit breakers are an important safety feature. They work the same way as the ones in your home. If a generator has an electrical fault, trips, this protects both the equipment and any people that may be working near the faulty equipment. Circuit breakers consisted of an oil tank with electrical contact switches inside, and it basically works like a circuit, right? Open and close the circuit. All the tools, wrenches, spud wrenches. You see how these 4 turbines all look fairly similar to each other? Well, they are similar, they're the same design. So they were all put in together at the same time. This one was put in by itself at a later date. You'd see it's kind of a different design, different penstock. So you can't see the penstocks on these ones, but you can here. So this is a penstock. This is what is supplying the turbine with water, right? You can see, kind of looks like a turbo almost, but it's not, it's a turbine. And that's where the water comes in. Once the water comes in, spins the shaft, which rotates all that. Generating Unit 5 in 1922, the potential for added water supply from Alouette Lake Tunnel, BC Electric decided to increase the capacity of the Stave Falls plant. On September 19th, 1925, they installed a 5th generating unit that could create extra 17,500 horsepower. The Unit 5 turbine was also double horizontal Francis type. Like the other 4 units, it had a scroll case that evenly distributed the water to the runner. This is a more efficient design than the pressure case, which is what the other turbines had. 10 commandments of the diesel operator. 8-cylinder diesel. 1, 2, 3, 4, 5, 6, 7, 8. Manifold. Synchronous generator, right? So it's a diesel generator. That's where they generated power. You got step down and step up transformers, right? One of the two. It's either one or the other. It's either stepping down or it's stepping up. Circuit breakers, transformers, generator. So it comes in, circuit breaker protects everything, gets stepped up to the generator, which then sends it to the switchyard, which then sends it out to us. The original waterfall. IC transformers. These are beautiful, man. Absolutely beautiful. This is a really cool area. It feels like some kind of out of Star Trek or something. You'll see in a sec what I'm talking about. Penstock. So this is the penstock pipe, sample of the penstock pipe. Transformer, circuit breakers. Crazy artwork here going on. So yeah, this hallway, like the shape of this hallway is really weird. It feels like something like on a spaceship or something. And there's cool stuff in like all the pockets. Where they got everything, all displays from all over the province here. All kinds of cool stuff. Drill press. Machine shop. Oh, this is the Stave machine shop. Nice. Tools area, yeah. Maintenance, right? Very important. Ironing machine, okay, don't care about that. We're gonna go out to the switchboard now, and we're gonna go take a look at the switchboard, which is where the power comes from the transformer, comes out of here, bank number 7, 12 kilovolt, station service, copper wires that run small, no longer in service, to the bridge crane. Pot heads, type of insulator with a bell-like pot shape that used to connect the underground electrical cables to overhead power lines. Good old pot heads, eh? Once the power gets upstepped, comes over to here. That's the tail race. So this is where the water would exit once it's done doing its thing, and then it would be down the river there. Delivering power to the people. Comes out of the plant, goes into the transformer, gets upstepped, comes all the way down, goes back to the substation, gets stepped down again, travels, comes into your house. So this is the switchyard. The switchyard contained all the equipment needed to move the electricity from the powerhouse to Stave Falls at various substations. Originally, this equipment was called switchgear, was housed inside the powerhouse building. With the installation of Unit 5 and the increased output, more switchgear was needed. There wasn't enough room indoors, and it was installed outside. The switchgear has been located on the roof, but later moved down here. Buswork is the name given to the conductors in the powerhouse and switchyard. The thick metal wires called transmission or distribution lines. After they leave the switchyard, the steel structure, which is columns of trusses that supports the insulators, disconnects the switches, and the bus is the only small piece of the original buswork. More than 100,000 kilograms of steel. The green structure is the transformer for Unit 4. The transformer is used to increase the voltage from 4,400 to 60,000 volts to help the power travel the long distance. The brown discs are the insulators. So all these little brown discs you see, those are all insulators. And then these are the transformers, and they're really just upstepping the current with those transformers we saw inside the powerhouse. And then it comes out to here, and then it moves on up. So this is the transformers, the switchyard, and those are all just insulators. So this is an electric car, Detroit Electric. One of the first electric cars, 1913 Detroit Electric. Anderson Electric Carriage Company. The batteries is 64 nickel iron alkaline cells, arranged in 2 banks, wood artillery type wheels, faux radiator, motor generator charger, distinctive tiller type control. See the cells. Been around for a while. So that's the electric car, Detroit Electric. So that's the Blind Slough Spillway. It's a dual dam, right? So this is the old complex where they're producing power. Penstocks over here. Old dam, new dam, where they have the new turbines, new Stave Powerhouse, 2 Kaplan turbines, and then you've got the Blind Slough Dam, and that's their spillway. So if this was to flood here, they would open these gates up, these sluice gates, and the water would come down through here. So that's the Blind Slough Dam. Okay, so Tesla, guys. The man himself there. 1856 to 1943, Nikola Tesla patented over 100 machines and created over 700 inventions. He was the driving force behind a new way to transmit electricity using alternating current. He also designed the induction motor. He invented the neon and fluorescent bulbs, the automobile speedometer, and the ignition system, and the principles behind remote control, radio, radar, electronics, and the microwave oven. Ben Franklin saw his lightning strike there. He was the first guy to see electricity. Ben Franklin, the 10th son of 17 children, Boston soap maker, candle maker. In 1746, Franklin began to investigate electrical phenomenon. He discovered electricity by flying a kite in a thunderstorm. It isn't really true, but his experiments taught the world some new things about electricity. Michael Faraday. Born to a poor family in London, Faraday was curious and questioned everything. At age 13, he became an errand boy for a bookbinding shop in London. He read every book that he bound. He decided that one day he would write a book of his own. He became interested in the concept of energy, more specifically force. Faraday created his first electric motor in 1831. He showed that if you bend a long coil of wire into loops and then push a bar magnet into the coil, an electric current flows. If the magnet was pulled out of the coil, the current also flows, but in the opposite direction. If the magnet is pushed quickly in and out of the coil, the current flowing back and forth all the time. This is called alternating current, or AC. James Windhurst spent most of his professional career in the shipping industry as a surveyor evaluating ships. That's the Wimhurst machine. Alessandro Volta. You know the word volt, right? Well, that's the name after Alessandro Volta. 1881. Volta decided to become a physicist when he was only 14, so he was fascinated by electricity. He wrote poetry about it. In 1800, Volta piled up copper, zinc, cardboard soaked in salt water and attached a wire to the top and bottom of a Victaulic pile. He closed the circuit, electricity, that's the battery. He made the first battery, right here. That's the Tesla coil. High voltage transformer converts electricity into air. The reason it's purple is because it's burning nitrogen. And then the reason you were seeing these lights turn on is because the electromagnetic field is so strong from the Tesla coil that these fluorescent lights, it excites the gas in the lights and makes them glow, even though it's not connected. This is a Faraday cage. This prevents the electric current from coming out towards us. So Michael Faraday cage, this basically stops electric current from doing the damage it could do. That's the Tesla coil. Underwater power. Oh, this is subsea cable, yeah. Cool. 1,000 kilometers of submarine cables running under lakes, rivers, and the sea. Power is provided to Vancouver Island via 3 separate submarine crossings. The cable section shown here is used to carry 525,000 volts from the Sunshine Coast to Dunsmuir on Vancouver Island. The cable is 155 millimeters in diameter, weighs 75 kilos per meter, 400 meters below the surface. So that's the subsea cable. You can see all the different layers of it. Power capacity in there, right? Copper. That's what it looks like by itself. What is electricity? Electric charge, electric energy, free electrons that can flow around the circuit like water. It's just electrons, guys. We're just manipulating electrons here. Almost at the speed of light. It doesn't quite move at the speed of light. It almost moves at the speed of light. Sun energy. So right now, we have rotation night and day, and then we're going to do precession next, which is the season. So like you can see right now, it's wintertime. Right now, it's summertime. Curved slanting blades, like blades in a propeller, allows the air to push them, generates power. Revolutions per minute, 1,500. We got 5 volts, we're climbing here. And look, you can see now I got load on it. I'm using the electric motor. Look, the RPM's dropping, and then it goes back up. LED, let's see the load on this one. Oh, it's not affecting it too badly. What do we got? Incandescent light here. See, so they light up. Resistor, ooh, that does a really good job. Edison bulb. Englishman Warren de la Rue first developed the incandescent light bulb using platinum wire for filament in 1820. It was too expensive to be mass-produced. Oh yeah, Canadians Henry Woodward and Matthew Evans developed the carbon filament idea, sold their patent to Thomas Edison in 1875. 1879, Thomas Edison created the first commercially viable incandescent light bulb using carbonized bamboo filament in the vacuum. Jacob's ladder. This spark is about 150,000 volts. So you can see the contact, Jacob's ladder. Wimshurst machine generates static electricity by using 2 counter-rotating plastic discs to induce huge current. This process is rubbing your feet together on a carpet very fast. Static electricity is picked up by the brass brushes that sweep close to the surface of the disc. The brushes transfer the electrical charge through the brass balls into 2 Leyden jars located at the front and left corners of the machine. Leyden jars are able to store large amounts of electricity, almost 350,000 volts. When the jars are fully charged, they release the electricity suddenly between the 2 rods at the front of the machine. Alrighty guys, so we just finished up the Stave Powerhouse, as you can see right behind me there. Stave Powerhouse, that was incredible. Really cool to see the history of power generation. See a different format of power generation too, the horizontal turbines. You don't usually see that. And it literally just for ease of maintenance, you know, other things. But yeah guys, pretty good show. It was really cool to see everything. We've got more stuff coming. I'm gonna be doing the Revelstoke Dam and the Bennett Dam as well. Got a visitor's pass, so I'm gonna be hitting those up in the near future once they open. It's closed, the other ones are closed for the season, but this one's just outside Vancouver in Mission, just near Stave Lake. So we're gonna close it out here now. That's gonna be it for me guys. I hope you enjoyed the power video. Hope you enjoyed Stave Lake. And if you're ever in the area and you're looking for something to do, definitely worth a stop. So that'll be it for me guys. Sasquatch out.